Tonight, we're going to leave Earth's orbit and ride all the way to the edge of the Sun's influence on one of the most remarkable journeys in human history. Not in imagination alone, but alongside the only spacecraft that have actually gone there, through a region where the familiar rules of our solar system begin to break. For decades, scientists pictured that region as a lonely bubble, a self-contained solar system wrapped in a smooth shell of solar wind, drifting through almost empty space. A protective cocoon with a clear boundary, a neat edge, and nothing but thin interstellar gas beyond. Clean, simple, isolated. Reality did not cooperate. A new all-sky map has revealed that the solar system is not sealed inside a quiet bubble at all. It is wired into a vast, structured highway of particles and magnetic fields, a hidden interstellar traffic system wrapped around the heliosphere like glowing lanes on a cosmic freeway. No one expects a road network in the dark. Before we get started, picture the Voyagers at the beginning. 2 spacecraft launched in 1977, designed for a 5-year mission to study the giant planets Jupiter and Saturn. That was the plan. A quick grand tour, powered by a rare planetary alignment, then silence. They refused to retire. Nearly 50 years later, Voyager 1 and Voyager 2 are still talking, running on radioisotope power sources and transmitters weaker than a household light bulb. They have flown billions of miles beyond their original targets, past all the known planets, into the borderlands where the sun's wind meets the galaxy. And out there, they discovered that the edge of the solar system is not an edge at all. At the outer boundary of the heliosphere, where the solar wind slows and collides with the interstellar medium, Voyager's instruments began to see things that did not fit any model. The charged particles changed in unexpected ways. The magnetic field twisted into strange directions. The density of plasma jumped, then stayed high. Galactic cosmic rays surged in, as if a gate had opened in the dark. Prediction said smooth gradients and a simple, spherical frontier. Observation revealed sharp walls, tangled fields, and hints of channels where particles flowed as if guided along invisible rails. Those clues, combined with all-sky maps from missions like IBEX, pointed to something astonishing. The heliosphere may sit inside a filamented, magnetically organized structure that behaves like an interstellar highway around our solar system. By the end of tonight, you're going to understand how the heliosphere really looks, what this hidden highway is, and why it means the solar system is not nearly as isolated as the textbooks claimed. Now, let's begin. So if there's a hidden highway wrapped around the solar system, why did every textbook for decades show something so simple? A lonely bubble in space. A clean, round shell where the sun's influence ends and interstellar space begins. Before we get started on the weird data, remember the traditional picture. Scientists imagine the heliosphere as a mostly spherical protective bubble of solar wind, inflated around the sun like a soap bubble in air. Inside, solar particles, solar magnetic field, planets orbiting in a kind of cosmic safety zone. Outside, the interstellar medium, with its own particles and fields flowing past. Between them, a neat boundary. The termination shock where the solar wind slows, the heliopause where it stops. Beyond that, true interstellar space. Designed models put that boundary at roughly 90 to 100 astronomical units in every direction. A tidy number, a tidy shape. No one expects the real solar system to care about tidy. Then Voyager 1 and Voyager 2 reached the edge. The prediction versus observation gap exploded. Voyager 1 hit the termination shock not 75 or 80 astronomical units, but around 94 astronomical units. Voyager 2 crossed it closer in. Later, Voyager 1 finally crossed the heliopause at about 121 astronomical units. Voyager 2 crossed that same boundary, near 119 astronomical units, but in a different direction, under different solar conditions. Farther away than predicted in some directions, closer in others. The shape was completely wrong. If this were a simple bubble, the solar wind pressure and the outside pressure should balance in a predictable way. Instead, the data refused to behave. Magnetic fields twisted in unexpected alignments. At the heliopause, the field direction changed less than models said it should, hinting that the local interstellar magnetic field might already be threading through the boundary. Particle counts jumped and dropped sharply, but not in a clean, one-time step. There were regions where low-energy solar particles vanished, high-energy galactic cosmic rays surged, and yet the magnetic field still looked solar, zones that looked at the same time both inside and outside the solar system. No one predicts a boundary that acts like that. Tonight, we're going to turn those contradictions into a roadmap. Because hidden inside this messy data are 7 revelations: the true shape of the heliosphere, which may look less like a comet tail and more like a distorted croissant; the mysterious ribbon in the sky that IBEX discovered, a glowing band of energetic neutral atoms aligned with the local interstellar magnetic field; the role of that external field in sculpting the entire heliosphere; the existence of a structured, possibly filamented tail stretching behind the solar system, a particle highway where charged particles slide along magnetic lanes, the real edge of the solar system, which is not where the old diagrams placed it, and what all of this means for travel between stars. If our bubble is distorted, pierced, and threaded by external fields, then what are those threads really doing? Are they just guiding particles, or are they outlining natural lanes that future spacecraft could ride between worlds and beyond? The next maps forced scientists to confront that possibility. The next surprise is not at the edge of the solar system, but in the space beyond it. For decades, that space was treated as an afterthought, a background, a nearly empty void between stars where a thin gas drifted, magnetic fields wandered randomly, and nothing like a road or a lane could even exist. That picture feels safe. Clean boundary, simple outside. The sun blows a solar wind, it carves a bubble, and beyond that bubble is just a quiet interstellar medium. Low density, weak fields, no structure. That is the diagram every student sees. That is the environment every early model of interstellar travel assumes. You leave the heliosphere, and you enter a featureless ocean. Then a spacecraft that never left Earth orbit redrew the map. NASA's IBEX mission was launched to do something subtle: count energetic neutral atoms coming from all directions in space, not glamorous, not a grand tour of planets. But when scientists stitched those counts into an all-sky image, they discovered a feature absolutely no one anticipates: a bright, narrow band encircling the entire sky, a ribbon of emission, thin and sharp, cutting across constellations. Prediction: a mostly uniform glow, maybe a few patches. Observation: a glaring structure, brighter than everything around it, wrapped right around the heliosphere like a cosmic belt. Tonight we're going to treat that ribbon for what it really is: a signpost. Because the pattern is not random. The ribbon lines up almost perfectly with the direction of the local interstellar magnetic field. That means those atoms are tracing where charged particles are being organized, guided and focused by invisible magnetic rails. Think of charged particles as traffic in space. They do not wander freely. They spiral along magnetic field lines, bunch up where those lines bend, and thin out where the fields open. IBEX is not seeing the particles directly. It is seeing their fingerprints, energetic neutrals created when the solar wind collides with the interstellar medium along preferred pathways. In other words, the ribbon is not just a pretty feature. It is a flow pattern, a lane, a place where the galactic wind and the solar wind are negotiating, and where the magnetic field is steering that negotiation into a narrow band. Now, let's begin to appreciate what that means. Our solar system is not drifting alone through empty space. It is embedded in a larger network, filaments of gas, clouds of plasma, and magnetic channels that thread between nearby stars. The heliosphere is a node in a web, not an isolated bubble. By the end of tonight, you're going to understand why that is such a radical shift. If there are lanes where particles naturally concentrate, there may be regions where radiation is harsher and others where it is shielded. There may be directions where future spacecraft can ride existing flows, and others where they must fight against them. No one expects a hidden highway to appear in what used to be called empty space. Yet IBEX's ribbon, Voyager's boundary crossings, and new 3D simulations are all pointing to the same conclusion. The local galactic neighborhood is connected, structured, and dynamic. In the next sections, those separate clues will be pulled together into a single shocking map of how our solar system plugs into the larger interstellar network. Those separate clues are about to lock together into a single picture. But the fact that you're still here, following the twists in this map of invisible fields and particles, says something important about you. You're not just watching a video about space. You're the kind of person who wants to understand what really lies beyond the planets, past the neat diagrams in a textbook, out where the solar wind thins into the interstellar medium and the word boundary stops being simple. Most people are satisfied with the old image, a round bubble, a hard edge, empty space beyond. You're still here while scientists argue about croissant shapes, comet tails, and a hidden highway wrapped around the solar system. That curiosity is rare, and it quietly changes what missions get explained, what data gets visualized, and which questions get asked out loud. Before we get started on the next layer of this story, there's something crucial that has to be said. Deep dive videos about Voyager, IBEX, IMAP, and the heliosphere are not easy to make. Each number, each field line, each ribbon on a map comes from technical papers, archived telemetry, and models that were never designed to be unpacked in plain language. No one expects a 1970s spacecraft with kilobytes of memory to still be rewriting how the solar system connects to the galaxy. No one predicts that a small spacecraft in Earth orbit, counting energetic neutral atoms, will reveal a structure that looks like a galactic traffic lane. Turning those surprises into something clear and accurate takes time. Here is where you come in. When you like this video, subscribe, or leave a comment, the algorithm quietly tags you as someone who wants more than surface-level space content. That signal matters. It tells the system to show this to more people who think the same way. So take a second right now to tap like, to subscribe if you haven't already, or to drop a comment about what you thought the edge of the solar system was before watching. A clean bubble? A hard wall? Just nothing beyond Pluto? That single action is low friction for you, but it has real impact. Because more engagement does not just grow a channel, it justifies more ambitious breakdowns of missions, data, and simulations that almost never leave specialist conferences. It means more time spent turning IBEX sky maps into something intuitive, more careful passes through Voyager's magnetic field readings, more visualizations of how solar wind and interstellar wind braid together. Tonight we're going to keep pushing that. By the end of tonight you're going to understand how a few aging spacecraft and a handful of sky maps exposed a hidden interstellar network around us. Now, let's begin. To understand how we got here, how we ended up mapping a hidden interstellar highway without ever leaving Earth's orbit, we need to go back to 1977. So when the story jumps back to 1977, it is not nostalgia. It is the moment the keys to that hidden highway are quietly rolled out onto a Florida launch pad. Cape Canaveral, late summer heat. Two nearly identical spacecraft, each about the size of a small car standing under the gantries. Tonight we're going to watch them leave, knowing what almost no one on that beach can imagine. These machines will end up far beyond the traditional boundary of the solar system. The sequence is already strange. Voyager 2 goes first, on August 20th. Voyager 1 follows on September 5th. The numbering looks wrong. It feels like a mistake. But this is where the logic of deep space takes over. Voyager 1 is launched second, yet placed on a faster, steeper trajectory. Its path bends harder through the Sun's gravity and Jupiter's pull, so it will reach Jupiter and Saturn before Voyager 2. Arrival order, not launch order, sets the names. In a sense, the numbering is a prediction about who will win a race around two giant planets. Look closer at one of these spacecraft. About 800 kilograms, a 3.7 meter high-gain antenna like a white dish, locked on Earth across billions of kilometers, 3 radioisotope thermoelectric generators, warm blocks of plutonium dioxide turning nuclear decay heat into a slow, steady trickle of electrical power. Around the central bus, a ring of instruments, magnetometers for fields, detectors for charged particles and cosmic rays, plasma analyzers to taste the solar wind, cameras and spectrometers to image worlds no human has ever seen up close. On paper, the mission is modest. 5 years. Jupiter and Saturn, then a long quiet fade into the dark. But the real reason these particular spacecraft exist is a celestial accident that happens only once every 176 years. In the late 1970s, the 4 giant planets line up in such a way that a single spacecraft can hop from one to the next, using gravity assist to steal orbital energy and change course without carrying enormous fuel tanks. This is the Grand Tour concept. Jupiter bends and accelerates you towards Saturn. Saturn can fling you toward Uranus. Uranus can send you onto Neptune. Each flyby, both a destination and a maneuver. Without that alignment, visiting all 4 giant planets would be an entirely different problem. Separate missions, decades between encounters, vastly more money. No clean, continuous arc from the inner solar system out toward the edge of the heliosphere, and no natural stepping stone from the last planet to interstellar space. Before we get started on what they actually discovered out there, it helps to see the stakes. Miss this launch window, and the Grand Tour vanishes for generations. Catch it, and 2 car-sized machines can ride a gravitational conveyor belt that leads, eventually, to the very skin of the sun's influence. By the end of tonight, you're going to understand how that choice to exploit a once-in-centuries alignment turned a short planetary mission into humanity's first passage onto the interstellar highway. The original plan is simple. 5 years, 2 giant planets, then a long quiet fade into the dark. Voyager's primary mission is written almost like an expiration date. Swing past Jupiter, steer through Saturn, record images, magnetic fields, charged particles, the solar wind, beam everything back through a 23-watt transmitter and a computer with tens of kilobytes of memory. After that, the expectation is straightforward. Power drops, instruments shut down, the spacecraft drift beyond the outer solar system as silent metal fossils. No one expects these machines to become permanent citizens of space. No one predicts that a 5-year mission will stretch into a 50-year conversation with the galaxy. And absolutely no one anticipates that their most important discoveries will happen long after the cameras stop taking pictures of planets. In 1977, engineers sign off on designs that only need to survive a handful of Earth orbits around the Sun. Components are tested for radiation, for vacuum, for the cold, but not for half a century of it. The missions are constrained by budgets, launch windows, and the brutal realities of 1970s electronics. Redundancy is limited. Memory is tiny. The whole system is tuned for that brief grand tour, not for a slow crawl toward the edge of interstellar space. Now, jump cut. The calendar reads decades later. The launch pads are museum pieces. Many of the original scientists are retired or gone, yet both spacecraft are still transmitting more than 20 billion kilometers from the Sun, where the solar wind is thin, the light is weak, and the radio signal that left Voyager yesterday will not reach Earth until tomorrow. Tonight, we're going to treat that contrast as the real plot twist. Designed for a short sprint between planets, still running in the cold, dark marathon beyond. For most of the 20th century, the edge of the solar system is drawn like a neat shell. There is the Sun, the planets, the Kuiper belt, and then a crisp boundary where the solar wind stops and real interstellar space begins. A protective bubble, a clear inside and outside. By the end of tonight, you're going to understand why that picture had to be torn up. Voyager reveals that the frontier is not a wall, it is a landscape. First comes the termination shock, where the supersonic solar wind slams into the interstellar medium and slows. Beyond that lies the heliosheath, a turbulent, compressed region where particles and fields twist together. Farther out still waits the heliopause, the shifting boundary where the sun's influence finally loses its grip and the galaxy's magnetic field takes over. The most paradigm-shifting discoveries do not arrive at Jupiter's swirling storms or Saturn's rings, but in these dark regions where there are no planets to photograph. Here, the spacecraft feel the solar wind weaken, detect galactic cosmic rays rising, and measure magnetic fields that no model truly predicted. The edge of the solar system turns out to be a layered dynamic frontier that Voyager will trace not with dramatic flybys, but with slow, patient steps into the night. Now, let's begin to follow those steps toward the place where our space ends, and the interstellar highway starts to appear. Those slow, patient steps are walking toward a border that, for most of the 20th century, looked deceptively simple. In every textbook diagram, the edge of the solar system was a clean line, a neat shell drawn with the confidence of a cartographer who thinks the map is finished. Before we get started with what Voyager actually found, it helps to see the picture everyone carried in their heads. The sun sat at the center, solar wind streaming out in all directions, inflating an almost spherical bubble in space. In front, along the sun's direction of motion through the galaxy, artists drew a bright bow shock, like the wave piling up in front of a ship. Behind, they sketched a long, graceful, comet-like tail trailing off into the darkness. It looked elegant. It looked inevitable. The physics seemed straightforward. The solar wind races outward until its pressure finally balances the thin gas of the local interstellar medium. Where that supersonic wind slows abruptly, models placed a smooth termination shock. Just beyond that, they drew a thin, crisp heliopause, the final boundary where the last traces of solar plasma give way to interstellar space. By the end of tonight, you're going to understand how bold that simplicity really was. In those early models, equations treated the plasma as a fluid, averaged over directions, with the sun's magnetic field stretched neatly into spirals. The interstellar medium was often treated the same way, a gentle headwind with uniform pressure and a background magnetic field that nudged, rather than carved, the heliosphere. Scientists trusted these pictures. They appeared in late 20th century astronomy textbooks, in planetarium shows, on posters in classrooms. Mission planners used them. Animations for the Voyager mission showed the spacecraft cruising toward that tidy shell, crossing one clean shock, then exiting into a calm, well-defined beyond. Outside a small circle of plasma physicists arguing over details in journals, almost no one questioned the overall shape. But underneath that confidence was a glaring blind spot. There were almost no in situ measurements far from the ecliptic, and none beyond the giant planets. All the data came from spacecraft orbiting near the plane of the planets, or from remote sensing of energetic particles and radio waves. Those diagrams were informed guesses, not hard maps. The bow shock had never been seen. The tail had never been sampled. The heliopause was a line on paper, not yet a place in space. Tonight we're going to see what happens when drawings meet reality. Voyager would fly not through an idealized fluid, but through a tangled, magnetized frontier. IBEX would later map energetic neutral atoms and reveal a mysterious ribbon wrapped around the heliosphere. New simulations would show a heliosphere that is squashed, twisted, maybe even croissant-shaped, threaded by external magnetic fields. No one expects the real border to look anything like the tidy bubble we drew. The question is, what did the spacecraft actually run into when they reached that misdrawn edge? To understand that misdrawn edge, you have to meet the thing that drew it in the first place. The heliosphere is not just a passive bubble floating in space. It is being inflated from the inside by a relentless, invisible hurricane. That hurricane is the solar wind. Not wind like air, but a supersonic stream of charged particles mostly protons and electrons, racing outward from the sun's corona in every direction. This plasma is so hot and so fast that it simply cannot remain bound to the sun. It escapes, carrying the sun's magnetic field with it, and fills the entire solar system. Near Earth, this wind typically blows at hundreds of kilometers per second. Slow streams cruise at around 300 to 400 kilometers per second. Fast streams roar past 700 or even 800 kilometers per second. The temperatures are brutal, hundreds of thousands of degrees, yet the density is incredibly low. Just a few particles per cubic centimeter near our orbit, thinning out as you move beyond the planets, but still organized enough to drag magnetic field lines across billions of kilometers. Before we get started with exotic heliosphere shapes and interstellar highways, this is the engine, the constant outflow that pushes back the galaxy. By the end of tonight, you're going to understand that the border Voyager crossed is really where this wind finally loses the fight. In the 1950s, almost no one expects this. The dominant picture imagines the corona as a static, glowing atmosphere clinging to the sun. Then a young physicist named Eugene Parker runs the numbers and finds that a hot corona like that cannot just sit there. The gas pressure is too high. It must expand into space as a continuous flow. Parker predicts a solar wind, supersonic, persistent, sculpting the entire system. Reviewers reject his paper. The idea seems too radical. Yet early spacecraft in the 1960s detect exactly what he described, turning a controversial calculation into the foundation of modern heliophysics. Every second, this wind removes mass from the sun. About 1 million tons of material leave via the solar wind every second. That sounds catastrophic. But the sun is so massive that over billions of years, this loss barely dents its total mass. The star keeps shining, the outflow keeps blowing, the bubble keeps growing. Tonight we're going to see that this is not just a local breeze. As the solar wind rushes outward, it eventually slams into the thin gas and magnetic field between the stars. That collision carves out a cavity in the interstellar medium, a teardrop or croissant-shaped heliosphere whose true boundary, Voyager and IBEX have been trying to trace. Now, let's begin to follow that wind outward to where it slows, piles up, and finally yields to the galactic environment beyond. The solar wind does not just fade away into the dark, it hits a wall. Not a solid wall of rock or metal, but a wall of pressure. Tonight, we're going to walk that invisible frontier step by step, because by the end of tonight, you're going to understand why Voyager's last great discoveries only make sense if you can picture the layers of this strange, inflated boundary. Follow that wind outward. Close to the sun, it races faster than sound in that plasma, supersonic, carrying the sun's magnetic field with it. But hundreds of times farther from the sun than Earth, the interstellar medium pushes back hard enough that the solar wind can no longer outrun the pressure ahead. It hits a standing shock wave. That is the termination shock. At the termination shock, the solar wind suddenly slows from supersonic to subsonic speeds. Its particles heat up, its magnetic field kinks, and its smooth flow becomes turbulent. Scientists had predicted this transition for decades, but when Voyager 1 actually crossed it, the distance was wrong, the strength was different, and the shock itself was patchy and moving. No one predicts a perfectly clean line anymore. This is a wrinkled, shifting frontier. Beyond that shock lies the heliosheath, a kind of cosmic buffer zone. Here the slowed solar wind piles up, compresses and swirls. Magnetic fields twist into eddies. Blobs of plasma collide. Energetic particles ricochet through this turbulent region, gaining and losing energy as they scatter. To the spacecraft, the heliosheath is noisy space. Fluctuating particle counts, changing directions, a constant argument between the sun's outflow and the galactic environment beyond. Keep going outward, and the pressure balance tips. There is a place where the outward push of the solar wind and the inward squeeze of the local interstellar medium match. That surface is called the heliopause. On the solar side, the sun's plasma still dominates, though it is slow and battered. On the far side, the sun's wind effectively stops flowing outward. The heliopause is not a physical shell, but it is the closest thing the solar system has to a skin. Beyond that skin, the plasma and magnetic fields do not belong to the sun at all. The spacecraft enter the local interstellar medium, material shaped by supernovae, distant stars, and the galaxy's own magnetic field. The particle densities jump, the magnetic field direction shifts, and the wind now comes from the galaxy as the entire solar system plows through it. Before we get started on the new maps and that hidden interstellar highway, hold one more idea. None of these boundaries are rigid. They are wavy, dynamic surfaces that flex with solar storms, sag where the interstellar pressure is higher, and ripple as the sun moves through space. The heliosphere is not a static bubble. It is a living interface, and those ripples are where the next mystery begins. The heliosphere is not a static bubble. It is a living interface, and those ripples are where the next mystery begins. Because outside that wrinkled boundary, space is not empty at all. Tonight we're going to step just beyond the solar system's skin and look at what it is actually pushing into. For decades, many scientists pictured the interstellar medium as a thin, uniform fog, a gentle background gas, the same in every direction, that the solar wind simply ploughed through. That expectation does not survive contact with the data. The reality is a patchwork. The local interstellar medium around the Sun is a quilt of partially ionized gas, dust grains, and magnetic fields stitched together into clouds, cavities, and filaments. Densities change from region to region. Temperatures shift. The magnetic field twists. By the end of tonight, you're going to understand that the solar system is not drifting through nothing. It is moving through a structured environment that can shape every boundary it creates. Right now, the Sun resides in, or right on the edge of, a feature called the Local Interstellar Cloud. This cloud is only a few light years across, but on human scales that is an enormous neighbourhood. Its density is about 0.1 atoms per cubic centimetre. That sounds unimaginably empty, until you compare it to the solar wind at the heliopause, where densities can drop to 1,000 times less. Out there, the cloud is actually the denser fluid, pressing back on the expanding wind. But the real game changer is not just the gas. Threaded through these local clouds are interstellar magnetic fields. They are not random. They form large-scale lines and filaments that can stretch for dozens, even hundreds of light years. Charged particles fill those fields like rails. They spiral, slide, and drift along them, turning invisible magnetism into preferred routes for cosmic rays and plasma flows. Think of these magnetic lines as train tracks crossing the galaxy, or as jet streams in Earth's atmosphere, narrow rivers of fast air that guide storms and steering currents thousands of kilometers away. In the same way, interstellar field lines create channels where particles race more easily, and dead zones where motion is resisted. No one predicts that such delicate structures could end up dictating how the edge of our solar system behaves. Yet that is exactly what the measurements point to. So when the heliosphere pushes into this magnetized medium, it does not just carve out a clean cavity. It gets wrapped, squeezed, and subtly connected to that larger network. The solar wind's bubble is draped over those magnetic tracks, tied into filaments that extend far beyond the planets. Before we get started on the new maps, hold that image. A moving star, its plasma envelope wired into a galactic grid. Because the next observation will show that those wires are not just theoretical. They light up. Those wires light up because the heliosphere is not a quiet, gentle bubble. It's a bubble under pressure. And once pressure enters the story, geometry stops being simple. Now let's begin with the most basic tug-of-war in this entire system. On one side, the solar wind, racing outward from the sun in all directions, hundreds of kilometers per second, a continuous outflow of plasma trying to inflate the bubble. On the other side, the local interstellar medium, that thin gas and dust and magnetic field outside pushing back. Where those pressures balance, you get a boundary. If the sun were sitting still in space, bathing in a uniform interstellar sea, that boundary might be nearly spherical. But the sun is not still. It's ploughing through the galaxy at about 26 kilometers per second, carrying every planet and spacecraft along for the ride. From the sun's point of view, there's a headwind, a galactic breeze slamming into the front of the heliosphere. That motion changes everything. The front of the bubble is rammed, compressed, and heated. The back is stretched out, pulled into a trailing wake. Think less perfect ball and more windswept droplet, like a raindrop leaning into the wind on a car windshield. By the end of tonight, you're going to understand why no serious heliospheric model today treats it as a simple sphere. But pressure from particles is only half the story. Magnetic fields add their own invisible architecture. The sun's magnetic field is dragged outward by the solar wind, wound into a huge spiral. The galaxy's magnetic field threads through the local interstellar medium at a different angle. Where they meet, they don't just add, they twist, drape, and pull on each other. Magnetic fields carry both pressure and tension. They resist being bent like stretched rubber bands in space. That tension can squash the heliosphere in some directions and elongate it in others, producing kinks and folds that simple fluid models completely miss. No one expects pure gas dynamics to capture what is, at its core, an electromagnetic structure. For decades, competing models tried to capture this complexity. Early on, many scientists favoured a classic comet shape, a blunt nose facing into the interstellar wind, and a single, long tail streaming behind, tens of astronomical units wide and hundreds long. Later, more sophisticated simulations, including the sun's rotating magnetic field, predicted something stranger. Instead of one smooth tail, the magnetic tension pinched the flow into separate lobes. A croissant, or multi-lobed heliosphere, with twin plumes of solar wind peeling off like exhaust streams from a jet. No one predicts that shape from simple intuition. It drops out only when the full magnetic geometry is allowed to fight against plasma pressure. So even before the new all-sky maps, theorists already suspected that the heliosphere was contorted, asymmetric, and wired into the galactic field. What they lacked was a global view. Voyager gave 2 narrow exit wounds. To really see the structure of flows around the heliosphere, scientists needed a mission that could image the whole boundary at once. Tonight, we're going to watch that global map come into focus, and it will not look like any textbook bubble. To really see the structure, scientists needed a global map. But before that map could be drawn, one spacecraft had to punch through the first wall. The moment came in December 2004 when Voyager 1 reached about 94 astronomical units from the Sun and quietly crossed a line no one had ever visited, the termination shock. Before we get started, picture what that means. 1 astronomical unit is the distance from Earth to the Sun. 94 of those is more than 14 billion kilometers out, far beyond the orbits of all the giant planets. Models had placed the shock closer in, maybe 75 to 90 astronomical units. Prediction versus observation again. The boundary was farther, thicker, and stranger than every scientist expected. The termination shock is where the solar wind finally loses. Inside, the wind is supersonic, racing outward at hundreds of kilometers per second, a hot plasma streaming from the sun. At the shock, it slams into the pressure of the interstellar medium and is forced to slow down, heat up, and compress. Voyager 1 rode straight through this invisible surf zone, and its instruments recorded the change. The solar wind speed dropped. Not gradually, but in a series of steps, falling from hundreds of kilometers per second to less than half that. At the same time, the plasma density jumped and the temperature soared, exactly what a shockwave in space should do. energetic particle detectors saw populations of charged particles suddenly reshuffled, with new, more intense fluxes of so-called termination shock particles appearing from directions that did not match the simple textbook picture. No one expects a 1970s spacecraft with tens of kilobytes of memory to rewrite the structure of the solar system. Yet that is what this crossing began to do. The data said the inner heliosphere was not ending with a neat spherical shock at a fixed radius. It was lumpy, dynamic, and clearly responding to both the solar cycle and the flow of the interstellar medium outside. Then Voyager 2 delivered the twist. In 2007, it reached the termination shock under different solar conditions and crossed at a different distance, around 84 astronomical units, 10 astronomical units closer to the Sun. Same mission, similar instruments, different exit wound. Instantly, it was clear. This boundary was not a perfect shell centered on the Sun. It was distorted, asymmetric, and probably being pushed and pulled by the external galactic field and the local interstellar wind. Beyond that shock lay the heliosheath, the subsonic region where the slowed solar wind piles up before meeting interstellar space. By the end of tonight, you're going to understand why this zone became one of the biggest surprises of the entire mission. It was thicker than models predicted, more turbulent, and full of puzzling flows and particle distributions that refused to line up with simple, smooth bubble diagrams. Now let's begin to follow Voyager into that chaos, because if the inner boundary was already misbehaving, the true edge of the heliosphere was almost certainly going to break the rules even more. So when Voyager 1 finally claws its way through that chaotic heliosheath, the stage is set for one of the most dramatic moments in the history of the mission. It is 2012, almost 35 years after launch. The spacecraft is more than 120 astronomical units from the Sun, over 18 billion kilometers out, far beyond the outer planets, where sunlight is a pale, anemic glow. Its cameras are long dead, powered down decades earlier to save energy, but the ears of the spacecraft are still open. Particle detectors, magnetometers, plasma wave instruments, silent metal listening to a nearly perfect vacuum. Tonight we're going to stand beside it, in imagination, and watch what happens when that silence suddenly changes. For years, scientists expected a clean, almost textbook signature when Voyager 1 hit the heliopause, the outer boundary where the solar wind yields to the interstellar medium. Solar particles would drop, galactic cosmic rays would surge, the magnetic field would twist to match the galaxy's direction, a neat line, a clear crossing. No one expects what actually arrives in the data. In late August 2012, the counts of energetic particles born in the Sun's wind plunge. Not gradually, sharply. Within days, intensities fall by more than a factor of 1,000. At the same time, the detectors watching high-energy galactic cosmic rays see the opposite pattern. A spike. A sudden, sustained increase in particles that have been wandering the galaxy for millions of years, now streaming into the solar system with far less resistance. Then comes the strangest clue of all. The plasma wave instrument hears a faint rising tone triggered by distant solar eruptions. From its frequency, scientists can infer the density of the surrounding plasma. The number is shocking, about 0.08 electrons per cubic centimetre. That is 2 to 3 times higher than in the heliosheath, and almost exactly what models predict for the local interstellar medium. By the end of tonight, you're going to understand why that single measurement forced everyone to rethink the edge of the solar system. There is only one problem. The magnetic field refuses to cooperate. Its strength jumps, as if the space outside is stiffer, more pressurized, but its direction barely rotates. Models had forecast a clear turn as Voyager left the Sun's magnetic bubble and aligned with the galaxy's large-scale field. Instead, the compass needle nudges, then holds, prediction versus observation, colliding in a few nanoteslas of stubborn data. So the debate ignites. Some scientists argue Voyager has entered a magnetic highway region, still inside the heliosphere, where field lines from the Sun connect directly to the interstellar field, letting galactic cosmic rays flood in while the geometry of the field itself has not fully changed. Others counter that the plasma density and particle populations are decisive. This is interstellar space. Over months, more events, more plasma tones, and more careful modelling converge on a consensus. Voyager 1 has crossed the heliopause into interstellar plasma, but the boundary has no crisp shell. It is tangled, layered, magnetically threaded back into the heliosphere. Absolutely no one anticipates a frontier that behaves like this, a porous, connected membrane instead of an isolated wall. And if the heliopause can leak and braid and share field lines with the galaxy, then the bubble view of our solar system is already broken. The real shock comes when a second spacecraft crosses on a different path, and distant telescopes start to map something even stranger wrapped around that boundary. So the bubble is leaking, the wall is braided, and the map is wrong. To fix it, scientists need a second cut through the boundary, not along Voyager 1's path, but from a different angle, with better sensors still online. That second blade is Voyager 2. Launched weeks after its twin, Voyager 2 took a different grand tour through the outer planets, then peeled off below the plane of the solar system. Same era, same mission family, completely different trajectory. And unlike Voyager 1, it carried a working plasma instrument all the way to the edge. When it finally crossed the heliopause in 2018, at about 119 astronomical units from the Sun, the entire field held its breath. This time, there was no ambiguous silence in the plasma channel. There was a clear, textbook-like signature. The solar wind particle counts plunged. The torrent of charged particles flowing outward from the Sun thinned, then dropped by more than an order of magnitude. At almost the same moment, the detectors watching for galactic cosmic rays saw the opposite trend, an abrupt, sustained rise in high-energy particles raining in from beyond the heliosphere. Pattern interrupt. The space outside is denser. That is not what intuition suggests when thinking about deep space. Voyager 2's plasma instrument could directly measure the density of the charge gas around it, instead of inferring it from oscillations like Voyager 1. The result was unmistakable. The plasma beyond the heliopause was several times denser than the solar wind just inside the boundary. The spacecraft had moved from the Sun's tenuous outflow into the compressed, gently flowing interstellar medium. Comparing the two crossings is like comparing two cuts through a storm front. Voyager 1 found a layered, leaky interface, with solar particles sneaking along magnetic field lines and strange, gradual changes in some energies. Voyager 2, in another direction, saw a sharper jump, a more sudden drop in solar wind, a cleaner increase in galactic cosmic rays, and a compact transition region only a few astronomical units thick in some measurements. Same global structure, different local behaviour. And yet the distances do not match. Voyager 1 crossed the heliopause at about 121 astronomical units. Voyager 2 at about 119. A few astronomical units might not sound like much, but for a boundary that was once modelled as a neat, nearly spherical shell, this offset is a red flag. It screams asymmetry. The heliosphere is being pushed, squeezed, and tilted by the external pressure of the local interstellar medium and the orientation of the galactic magnetic field. By the end of tonight, you're going to understand why that matters. The fact that the heliopause sits closer in Voyager 2's direction means the Sun's magnetic bubble is not a uniform shield. It is a wrinkled, magnetically connected interface, with folds and dents where external pressure is higher and magnetic field lines drape more tightly. Now, let's begin to see the implication. A wrinkled, draped boundary does not just sit there, it guides motion. Charged particles do not move randomly through space. They spiral along magnetic field lines, slide along gradients, and follow paths carved by pressure and geometry. If the heliopause is skewed and corrugated, then it naturally creates preferred lanes where particles can stream more easily. Tonight, we're going to follow those lanes. Because when distant telescopes start to map the sky in energetic neutral atoms, they do not see a smooth glow around the solar system. They see something that looks suspiciously like a road wrapped around our magnetic cocoon, hinting that this wrinkled edge is part of a much larger interstellar highway. To follow those lanes, you need a map. Not a single line traced by a lone spacecraft, but a full panorama of the invisible border wrapping the solar system. Tonight, we're going to switch from the Voyager's narrow road trip to a kind of cosmic weather satellite in Earth's backyard. The contrast is stark. Voyager 1 and 2 are like needles piercing the heliosphere along two thin, unrepeatable paths. Every magnetic flip, every change in plasma density is a point on a graph. Valuable, but local. They sample the boundary. They do not see it. To understand the global structure, scientists need something that can look outward in all directions at once without spending decades flying to the edge. That something is IBEX, the Interstellar Boundary Explorer. Launched in 2008 into a highly elliptical Earth orbit, this small spacecraft never travels beyond the immediate neighborhood of our planet. It simply loops around Earth, again and again. Yet from this vantage point, it produces all sky maps of the heliosphere's boundary. By the end of tonight, you're going to understand how a spacecraft that never leaves near Earth space can redraw the borders of the entire solar system. The trick is to stop chasing charged particles and start watching the ones that slip the leash. At the heliosphere's outer boundary, the solar wind slams into the interstellar medium. Protons from the solar wind collide with neutral atoms drifting in from interstellar space. In a tiny quantum-scale handshake, they exchange charge. The fast solar proton steals an electron, becoming an energetic neutral atom, an ENA. The original neutral becomes charged and is swept away by magnetic fields. Those newborn ENAs are the key. Because they are neutral, they ignore magnetic fields. They are not tied to spiraling field lines. They shoot off in straight lines, preserving the direction and energy they had at birth. Some of them head back toward the inner solar system, racing across tens of billions of kilometers until they cross IBEX's detectors. Now let's begin. Each time IBEX detects an ENA, it records its arrival direction and energy. One detection is a whisper. Millions build an image. By accumulating ENAs from every part of the sky, the mission reconstructs where they originated on the distant boundary, turning an invisible magnetic frontier into a global map of particle fluxes wrapped around the spacecraft. The goal is ambitious. IBEX charts ENA intensities across multiple energy bands, revealing where particles are being accelerated, where the solar wind is slowed and heated, and how that interaction changes with the solar cycle. No one predicts a simple picture, but most expect a somewhat smooth glow, tracing the compressed nose and extended tail of the heliosphere. What emerges on the first all-sky maps is anything but smooth. A narrow, bright band of ENA emission, arcing almost perfectly across the sky. A structure that aligns with the local interstellar magnetic field. A feature absolutely no one anticipates. The IBEX ribbon. And that ribbon looks less like a boundary line, and more like the illuminated edge of a hidden interstellar highway. It should be a footnote, a subtle gradient in the sky, a gentle fading of energetic neutral atoms as the solar wind runs out of steam. Instead, the very first IBEX all-sky map comes back, and looks like someone drew a luminous scar across the universe. A thin, blazing arc of emission. Not everywhere, not random. A narrow band wrapping almost perfectly around the sky like a glowing halo. If you could stand outside the solar system and see ENAs with your own eyes, it would look as if our entire neighborhood in space had been cinched by a cosmic belt. Before we get started on what it means, remember what scientists expect. Models say the heliosphere should imprint a mostly smooth pattern. Some regions a bit brighter where the solar wind piles up, some dimmer where it relaxes but nothing dramatic. Variations, yes. Dominant structures, no. Prediction versus observation could not be clearer. Designed to map a gentle glow, the mission instead finds a single feature that hijacks the whole sky. The ribbon is up to 3 times brighter than surrounding regions. It is so sharp, so concentrated, that the background almost feels like an afterthought. No one expects that. No one predicts that the most important structure IBEX will see is not the heliosphere's broad outline, but a mysterious lane running across its face, and absolutely no one anticipates how hard it will be to explain. At first, scientists do what they always do. They try to line it up with something familiar. Is it tied to the ecliptic plane, the flat disk where the planets orbit? No. Does it trace the galactic plane, the dense band of the Milky Way? Again, no. It ignores the solar system's obvious geometry, shrugs off the galaxy's most prominent structure, and sits at its own strange angle. For a while, the ribbon is a pure mystery, a traffic lane with no road, a signal with no clear source. But as more maps arrive, a pattern starts to emerge. The brightest parts of the ribbon seem to appear where the local interstellar magnetic field is perpendicular to our line of sight. That angle matters. When the magnetic field bends that way, charged particles from the solar wind and the medium beyond are more likely to be trapped, deflected, and funneled along those lines. Collisions there produce more ENAs, which then fly straight toward IBEX and light up the map. Tonight we're going to treat that ribbon as more than a curiosity. By the end of tonight, you're going to understand why many scientists now see it as the first global sign that the heliosphere is wrapped, squeezed, and guided by an external magnetic structure. Not an isolated bubble, but an object embedded in a larger current. In other words, the ribbon may be outlining a cosmic traffic lane, a preferred route where particles flow and interact around our solar system. The real question is, who else is using that lane, and where does it lead beyond our tiny patch of space? If that ribbon is a traffic lane, then the next step is to understand what lays down the road. In space, there are no painted lines, no asphalt, no guardrails. There are magnetic fields, and charged particles follow them. Now let's begin. Take a proton from the solar wind. It carries charge, it feels magnetic forces. Instead of flying straight, it corkscrews. It spirals around magnetic field lines while sliding along them, tracing out a helical path. Those invisible lines become natural guides, channels that tell particles where they are allowed to go and how fast they can stream beyond the heliosphere. By the end of tonight, you're going to understand why that matters at the edge of the solar system. The local interstellar magnetic field is not passive. As the solar wind pushes outward and the interstellar medium pushes back, that external field is forced to bend. It drapes around the heliosphere like a river flowing around a boulder, compressed and redirected right near the heliopause. Prediction versus observation again. Models once pictured a mostly smooth spherical boundary. IBEX and Voyager together revealed something more tangled. Near the heliopause, field lines crowd together, intensify and change direction. Particles from the galaxy and from the sun both feel that magnetic scaffolding, spiraling around it, sliding along it, rarely cutting straight across. Here is where the ribbon becomes more than a curiosity. Energetic neutral atoms are created when fast-charged particles steal electrons from slow neutrals. Where the draped magnetic field lines are oriented just right relative to the Sun and Earth, those charged particles are funneled back toward us before they neutralize. That geometry boosts ENA production in a narrow band across the sky, and that band is exactly where IBEX discovered the ribbon. No one expects a thin arc of enhanced particles to rewrite the architecture of the heliosphere. No one predicts that a mission never leaving Earth orbit would expose a hidden structure beyond Pluto, and absolutely no one anticipates that the brightest feature in the ENA sky would line up with the direction of the local interstellar magnetic field. Follow the logic. If particles spiral along field lines and those lines are draped, compressed, and aligned around the heliosphere, then there must be preferred regions where particles meet and trade energy. Regions where galactic cosmic rays pick up ions from the solar wind and neutral atoms all exchange accelerate, and stream along the same magnetic tracks. That is the definition of a transport network. So the ribbon is not just a pretty stripe on a false colour map. It is the visible cross-section of an interstellar highway system, a set of magnetically sculpted lanes wrapping around our solar system and plugging it into the broader galactic environment. The real surprise is what this implies. If there are highways, there might also be on-ramps, off-ramps, and junctions, and the next question is where those magnetic roads go once they leave our neighbourhood. Those magnetic roads sound like the domain of heroic deep space probes, racing through the dark to trace every lane. But here's the twist. The most detailed map of that interstellar highway did not come from Voyager at the edge. It came from a small spacecraft quietly looping just beyond Earth's magnetic shield. Pattern interrupt. Reset your mental image of exploration. Tonight we're going to step away from the romantic picture of a lone spacecraft fading into the black and look at a machine that mapped the frontier without ever leaving the neighbourhood. IBEX is not a Grand Tour Titan. No cameras, no flybys of giant planets, no gravity assists slingshotting it beyond the solar system. It is a compact spacecraft in a highly elliptical orbit around Earth, dipping close in, then swinging far out just beyond the magnetosphere, where the solar wind flows mostly unperturbed. That is where the trick happens. Voyager samples the boundary the hard way. One spacecraft, one path, one thin trajectory slicing through the heliosphere. Designed for a 5-year mission to study outer planets, it is still reporting from beyond the heliopause, but it only ever feels the conditions along 2 narrow tracks. IBEX does the opposite. From near Earth, it waits for the boundary to send information inward. The information arrives as energetic neutral atoms, ENOs, born when charged particles from the solar wind and the interstellar medium exchange charge and lose their electric leash. Because they are neutral, magnetic fields cannot steer them. They fly straight. Some of them head inward, racing across tens of billions of kilometers and slamming into IBEX's detectors. Each impact is a pixel in an invisible sky. Instead of a single cut through the boundary, IBEX builds an all-sky image, inside-out cartography. The spacecraft spins, the detectors count ENAs from every direction, and over months, then years, a global map of the heliosphere's skin emerges. The ribbon, the folds, the faint glow of the tail stretching away from the direction of the incoming interstellar wind. By the end of tonight, you're going to understand why that perspective is so powerful. Contrast the scales. Voyager is billions of miles out, with a radioisotope power source and a transmitter weaker than a refrigerator light. IBEX orbits a few Earth radii away, running on a modest budget and simple hardware. No one expects the cheaper near-Earth mission to redraw the solar system's boundary. No one predicts it will reveal a structure aligned with the galactic magnetic field that absolutely no one anticipates. And this technique is only the beginning. The next step is IMAP, the Interstellar Mapping and Acceleration Probe. Same inside-out strategy, far sharper vision, higher resolution ENA maps, repeated over time, watching the ribbon brighten, fade, and ripple as the solar wind breathes and the interstellar medium shifts. Now let's begin to connect this back to the highway. If the ribbon is just one bright lane in a larger magnetic road network, the obvious question returns with more force. What do the rest of those lanes look like, especially on the far side of the Sun, where no spacecraft has yet passed through the boundary at all? On the far side of the Sun, the mental picture used for decades is simple. The solar system is a comet, with the Sun at the head and a single, elegant tail of solar wind streaming behind it as we plough through the galaxy. One direction of motion, one long plume, one continuous wake fading into interstellar space. That image is clean. It is also wrong. Before we get started on the new view, remember why the old one felt so natural. The solar wind flows outward in all directions. The Sun moves through the local interstellar medium at tens of kilometers per second. and fluids in motion tend to form wakes. So scientists drew the heliosphere like a boat in a river, a rounded bow in front, a narrow tail behind, stretching for hundreds or thousands of astronomical units. Then came the pattern interrupt. Global simulations of the heliosphere, fed with better data on the Sun's magnetic field and the surrounding interstellar field, stopped producing a single, needle-thin tail. Instead, they started spitting out something stranger. The back of the heliosphere bulged, split, and wrapped into multiple lobes like a cosmic croissant. Magnetic tension lines twisted the solar wind into separate channels of outflow, not one unified exhaust. Tonight, we're going to stand in that wake and watch it break apart. In these newer models, charged particles from the Sun do not simply stream into one long corridor. They're guided along magnetic arcs that peel away into two main lobes, above and below the plane of the planets, with weaker turbulent flows in between. The tail is thicker, shorter, and far more structured than the classical comet sketch ever suggested. By the end of tonight, you're going to understand why this matters, and it starts with what was not seen. When IBEX and Cassini mapped energetic neutral atoms, they should have picked up a bright, elongated signature trailing far downstream if a huge tail were there. Instead, the ENA glow behind the Sun is muted, patchy, and surprisingly compact. The expected long, bright tail is missing. Prediction versus observation. One continuous wake versus a knotted, lumpy region that seems to end or fragment much sooner. The implication is stark. The heliosphere's tail may be short, or shredded, or broken into distinct streams that peel off into different directions of the local interstellar medium. In that picture, each lobe becomes its own lane. Some channels may connect more directly to the interstellar magnetic field above the solar system, others to regions below, creating preferred exit ramps for solar particles and preferred entrance ramps for galactic cosmic rays. No one predicts the tail would look like a three-dimensional highway interchange, but that is exactly what these models hint at. Ramps, overpasses, and cloverleaf loops where solar and galactic particles mix, merge, and are redirected. Now, let's begin to ask the dangerous question. If the hidden tail is already a tangled interchange, what happens when those lanes merge into the larger galactic network beyond? Those tangled interchanges in the tail are intriguing, but the real shock comes when a spacecraft actually drives onto one of those ramps and feels the traffic change in real time. That is exactly what happened to Voyager 1, years before scientists officially declared it beyond the solar system. In mid-2012, as Voyager 1 crept outward through the heliosheath, its instruments started reporting a pattern no one expects at the edge of a supposedly sealed bubble. The flux of energetic particles from the Sun, the familiar solar wind debris that had bathed the spacecraft for decades, began to plummet. At the same time, high-energy galactic cosmic rays from outside the heliosphere surged, inside particles down, outside particles up. But the magnetic field direction? Almost unchanged. That combination should not exist in a clean, sharp boundary. If Voyager had crossed a true wall, scientists expected everything to flip together. Field direction, particle populations, plasma conditions. Instead, the magnetic field lines around the spacecraft still pointed almost exactly the way they had inside the heliosphere, aligned with the solar magnetic spiral. Yet the particle mix looked like interstellar space. It was as if the traffic signs still said inside, while all the cars on the road were clearly from outside. This strange region was quickly given a name, the magnetic highway. Charged particles tied to magnetic field lines were suddenly able to stream away from the spacecraft, with almost no scattering, as if someone had cleared a lane. Solar origin energetic particles drained out along those lines. Galactic cosmic rays, guided by the same invisible tracks, flowed in. By the end of tonight, you're going to understand that this was not just an odd transitional zone. It was a physical demonstration of a magnetic on-ramp between domains. The simplest explanation is also the most radical for our picture of the solar system. In this highway region, field lines from the inner heliosphere and field lines from the local interstellar medium were connected, probably through magnetic reconnection. That connection let particles from both sides use the same paths, turning what had been imagined as a rigid border into a permeable interface. No one predicts a perfect polished wall here. Instead, the data screams structured frontier shaped by the draped interstellar magnetic field. This matters because it matches the broader highway picture emerging from IBEX maps and heliosphere models. If magnetic highway zones like the one Voyager 1 sampled lace around large portions of the heliopause, they form lanes where particles can efficiently travel between the galaxy and our solar system. Not random leaks, organized routes. Tonight, we're going to follow those routes outward. If one aging spacecraft can stumble onto a single on-ramp, what does the full interstellar highway network around the Sun really look like? Those routes are not empty, they are busy. Streaming along them are some of the most energetic travelers in the galaxy, galactic cosmic rays. These are not rays in the everyday sense, but individual charged particles, mostly protons and heavier nuclei, fired to near-light speed by supernova remnants, shock fronts, and other violent processes scattered across the Milky Way. Each one is a tiny bullet of energy, crossing light years, threading between stars and sometimes plunging straight through our solar system. If space were perfectly random, you would expect these particles to rain in from all directions with equal intensity, a uniform drizzle from the galaxy. But that is not what the data show. Ground-based detectors, satellites in Earth orbit, and now spacecraft far beyond the planets all see anisotropies, slight excesses from some directions, deficits from others. The pattern is subtle, often at the level of a fraction of a percent, yet it repeats. It hints that cosmic rays are being steered, nudged, and sometimes funneled by invisible magnetic structures around the Sun. Now let's begin to connect that to Voyager. Before we get started, remember where those spacecraft are. One is outside the heliosphere, one just beyond the heliopause, both riding the fading solar wind into interstellar space. Their particle detectors have watched cosmic ray intensities climb as the shielding of the heliosphere thins. Inside the heliosphere, the solar wind's magnetic field deflects and scatters many incoming galactic cosmic rays, lowering their intensity. Outside, that protection drops away, and the raw galactic spectrum appears. By the end of tonight, you're going to understand why that transition is not smooth. As Voyager 1 approached the boundary, it recorded sharp, step-like changes in cosmic ray counts. Some energies surged, others dipped, sometimes on timescales of days as the spacecraft crossed folds and wrinkles in the magnetic field. Then, in 2012, once it passed into interstellar space, the galactic component jumped and stayed high, while lower energy particles tied to the solar wind faded. The same story, with different details, played out when Voyager 2 crossed in 2018. No one expects those jumps to line up with anything as simple as a straight line in space. Yet when scientists compare Voyager's measurements with IBEX maps and models of the local interstellar magnetic field, a picture emerges. Regions where the field drapes smoothly around the heliosphere, especially near the ribbon, appear to be places where galactic cosmic rays slip in more easily. They are like preferred entry lanes, where the guardrail of the heliosphere is lower and the traffic can merge. In other directions, tangled fields and turbulent plasma act more like congestion, scattering particles, lengthening their paths, and reducing the flux that reaches the inner solar system. The result is a three-dimensional pattern of high-traffic corridors and low-traffic shadows, imprinted on the sky in the arrival directions of cosmic rays. Studying those patterns, scientists are not just counting particles. They are tracing the hidden geometry of the interstellar highway around the Sun. Each anisotropy is a painted line on the cosmic pavement, each sudden jump in intensity a sign for an unseen on-ramp or exit. But if cosmic rays reveal the lanes, what does the full map of that network look like when you step back and view the entire sky at once? To answer that, you have to look at something much quieter than cosmic rays. Tiny grains of dust, invisible atoms of helium and hydrogen. They drift in from beyond the solar system, slip past the planets, and glide right through the heliosphere. And in their directions and speeds, scientists have discovered another set of lanes painted into interstellar space. This is the pattern interrupt. The focus jumps from violent relativistic particles to slow neutral drifters. But these neutrals are perfect spies because they ignore magnetic fields. While charged particles are forced to follow the local field lines, neutral atoms and dust grains carry a cleaner imprint of the bulk flow of the surrounding medium. Track where they come from, and you track the motion of the interstellar wind itself. Missions like Ulysses and IBEX turn the entire solar system into a detector for this invisible current. Ulysses, looping over the poles of the Sun, repeatedly measured a stream of interstellar helium flowing into the inner system from a well-defined upwind direction. IBEX, orbiting close to Earth, watched energetic neutral atoms and also mapped the inflow of interstellar hydrogen. Both spacecraft agreed. There is a clear headwind, a preferred direction in the sky where the local interstellar medium seems to be blowing past the Sun. But the story does not stay that simple. Over decades, the measured upwind direction has shifted by a few degrees. The speed has nudged up and down. The ratio of helium to hydrogen has changed. Designed to see a steady, uniform breeze, these missions instead see subtle gusts, kinks, and shears. By the end of tonight, you're going to understand why that matters. Those variations are clues that the Sun is not ploughing through a smooth fog. It is threading its way through filamentary structures, strands or sheets where the density, temperature, and magnetic orientation of the gas all change together. One filament might carry slightly faster hydrogen, another a cooler mix of helium, a third more dust grains aligned in a different direction. As the solar system moves, it crosses these boundaries, and the inflow signatures twitch. Crucially, these filaments do not point randomly. Many appear to align with the local interstellar magnetic field, the same field that shapes the cosmic ray lanes and the IBEX ribbon. No one expects that alignment in a truly chaotic medium. No one predicts such coherence if the local space around the Sun is just a turbulent mess. The simplest explanation is a magnetically guided network, gas and dust organized along field lines, like traffic funneled into multi-lane highways. So the Sun is not only inside a bubble, it is embedded in a tangle of lanes, ramps, and intersections made of gas, dust, and fields. Tonight, we're going to follow that tangle outward, to see how those filaments connect to larger galactic structures and what that means for any future spacecraft trying to ride this hidden interstellar highway. Those filaments are not floating in isolation. They live inside a much larger structure, one that turns your whole idea of empty space into a kind of galactic architecture. Now, let's begin with your actual address in the Milky Way. Not just solar system, Orion arm, but something more precise. The Sun sits inside a vast cavity called the local bubble, a roughly 1,000 light-year wide hole in the galactic disk, filled with million-degree extremely tenuous gas. This is not a gentle environment. It was carved out by multiple ancient supernovae, overlapping shockwaves that pushed denser gas aside and left a glowing low-density void. From a distance, imagine a city block where several explosions have blown out the walls of neighbouring buildings, leaving one huge ragged atrium. That's the local bubble. The planets, the heliosphere, even the interstellar highway around it, all sit inside this hollowed-out region sculpted by dead stars. But the Sun is not floating in the middle of that void. It is currently near the edge of the local bubble, embedded in smaller, cooler clouds of gas and dust. The one wrapped around the heliosphere right now is called the Local Interstellar Cloud, or LIC. Just beyond lies another, the G Cloud. These are like denser fog banks drifting inside a hot, evacuated hall, and the solar wind is ploughing through their outer wisps. By the end of tonight, you're going to understand that these clouds are not just scenery. Their boundaries and the walls of the local bubble itself are threaded with magnetic fields. Those fields don't sit still. They loop, twist, and drape, forming large-scale walls and channels that guide gas and galactic cosmic rays, much like concrete barriers and overpasses steer traffic through a city. Here is the twist no one expects at first glance. The heliosphere is just one bubble moving through this maze. Its own magnetic shell and the interstellar highway mapped by IBEX are nested inside the local bubble's larger magnetic scaffolding. The ribbon around the solar system lines up with the local galactic field, which means the highway Voyager hinted at is only one interchange in a far bigger road system spanning hundreds of light years. From the Sun's point of view, there is a constant headwind from the LIC. From the galaxy's point of view, the Sun is drifting through a complex network of hot cavities, cooler clouds, and stitched-together magnetic seams. No one predicts a simple, static boundary in that situation, and absolutely no one anticipates a perfectly spherical shield. And this neighborhood is not permanent. As the solar system orbits the galactic center, it slowly migrates through these clouds and field configurations. Over millions of years, the heliosphere's size, shape, and the very on-ramps that connect it to the interstellar highway will change. The protective bubble that Voyager crossed is just a snapshot. So if the neighborhood evolves, what happens to the radiation, particles, and potential travel lanes that future spacecraft will encounter beyond the planets? So if the neighborhood changes, the lanes change. But those lanes also depend on something much closer to home, the actual shape of the heliosphere itself. And here, scientists don't just argue about details, they argue about the whole silhouette of the solar system's shield. The classic picture is deceptively simple. Imagine the Sun ploughing through the interstellar medium, the solar wind slamming into that galactic headwind and ballooning out into a blunt nose on the upstream side. Behind it, a long comet-like tail trails for hundreds or even thousands of astronomical units, with a bow shock ahead where the interstellar flow is forced to slow and divert. In that model, the interstellar highway looks like a multi-lane freeway wrapping around the nose, then squeezing into narrow, high-speed corridors far downstream along the tail. But prediction met observation, and the edges did not behave. IBEX did not see the clean, sharp bow shock that many expected. Voyager did not report a simple, gradual slide into a quiet tail. So a new vision emerged. In the croissant, or multi-lobed model, the Sun's magnetic field and the twisted magnetic tension in the solar wind pinch the downstream region into two broad lobes, like a cosmic pastry instead of a single, elegant tail. In that croissant-shaped heliosphere, the tail is shorter and more broken up. There is less of a single coherent wake and more of a double-lobed structure, with plasma and energetic particles looping around the flanks. The interstellar highway, in this picture, doesn't channel traffic only far behind the solar system. It creates preferred lanes around the sides of the heliosphere where field lines drape and reconnect, letting particles escape and enter along curved, magnetically guided routes. Then comes a third contender. Recent simulations tuned to Voyager's plasma densities and IBEX's all-sky maps suggest the heliosphere might be closer to a nearly bubble-like shape, with a thick, turbulent wake rather than a narrow tail. Instead of a sleek comet, think of a bullet moving through water, leaving a frothy, chaotic region behind. No one expects a neat, single stream in that case. No one predicts a simple boundary between inside and outside. In the bubble plus wake model, particle escape is messy but powerful. Magnetic field lines can peel away, fold back, and tangle, creating multiple on-ramps and off-ramps for the interstellar highway all around the heliopause. Some regions become quiet cul-de-sacs. Others become roaring express lanes where galactic cosmic rays and energetic neutral atoms are funneled straight toward the solar system. By the end of tonight, you're going to understand why this matters. Each proposed shape rearranges where those lanes concentrate, at the nose, along the flanks, deep in a tail, or in a broad turbulent wake. IBEX, Cassini, and the twin Voyager spacecraft are steadily ruling out the most extreme versions of each model, but a single agreed-upon geometry remains elusive. Now, let's begin to ask the dangerous question. How do you build a map of an interstellar highway when the very outline of your vehicle is still in doubt? You build it by launching a new cartographer, one that never leaves near-Earth space, yet redraws the borders of the entire solar system. NASA's Interstellar Mapping and Acceleration Probe, IMAP, is that cartographer. Planned for launch in the late 2020s, it takes the rough first draft sketches from IBEX and sharpens them into a high-definition atlas of the interstellar highway. Where IBEX saw the ribbon as a broad, glowing band of energetic neutral atoms, IMAP will dissect it, pixel by pixel, energy by energy, across a far wider range than its predecessor. Designed from the start as a follow-up to IBEX, IMAP upgrades almost everything that matters. Higher sensitivity, sharper angular resolution, broader energy coverage that extends both lower into the transition from the slow solar wind and higher into the realm where galactic cosmic rays begin to dominate. By the end of tonight, you're going to understand why that combination turns a static snapshot into a living, breathing movie of the heliosphere's boundary. IMAP will not cruise past the outer planets or plunge toward the heliopause. Instead, it will orbit around the Sun, Earth L1 point, about 1.5 million kilometers sunward of Earth. From there, it has an uninterrupted view of space in all directions, free from Earth's shadow and most of its magnetic interference. The spacecraft will slowly spin, sweeping its instruments across the sky, building all sky maps of energetic neutral atoms over and over again. That vantage point is crucial. At L1, IMAP can continuously monitor how the solar wind changes, how solar storms erupt, and how those variations ripple outward to the boundary regions Voyager only sampled along two thin tracks. No one expects a single crossing to tell the whole story of a structure that flexes and breathes with the 11-year solar cycle. IMAP's orbit turns time itself into a dimension of the map. The science goals are ambitious. IMAP is built to reveal how particles are accelerated at the heliosphere's outer boundaries, where the supersonic solar wind is slowed, deflected and heated as it encounters the local interstellar medium. It will track how the ribbon brightens, fades, and possibly shifts as the interstellar magnetic field and solar activity wrestle for control. It will measure how our heliosphere exchanges energy, momentum, and particles with the galactic environment beyond. Here's the pattern interrupt. The highway around the solar system is not fixed pavement, it's traffic. IMAP will effectively produce a dynamic, time-lapse map of that traffic, frame by frame, revealing how particle flow patterns twist with the solar cycle and with changing interstellar conditions that sweep past over years. Before we get started on where that leads for future missions, there's one more handoff to recognize. As the Voyagers age and their power dwindles, no one predicts their instruments will keep going forever. When those faint radio voices finally fall silent, absolutely no one anticipates the map-making to end. IMAP will be in place, not just to continue Voyager's legacy, but to vastly expand our cartography of the Sun's galactic surroundings. IMAP will expand the map. But the first discovery that really shattered the old picture came from two tiny spacecraft that simply refused to die. Tonight, we're going to stand with them at the edge of the solar system and watch that edge move. For decades, the mental image was clean. The Sun blows a steady solar wind. That wind carves out a bubble in interstellar space. At some fixed distance in every direction, the wind runs out of momentum and meets the interstellar medium. That was the heliopause, a neat spherical shell, a sharp boundary where solar space stopped and interstellar space began. Prediction versus reality could not have been more dramatic. Voyager 1 crossed the termination shock at 94 astronomical units, and the heliopause at about 121. Voyager 2 hit the shock at 84 astronomical units, and the heliopause at about 119. Same solar system, same star, different distances. No one expects the edge of a bubble to be tens of billions of miles closer on one side than the other. and the transition was not clean. As Voyager 1 approached the heliopause, the solar wind did not simply switch off. It slowed, it heated, it turned turbulent. The spacecraft saw layers, zones where energetic particles from the sun dropped, but galactic cosmic rays surged. Regions where magnetic field strength jumped, but the direction barely changed. Instead of a single line, the boundary behaved like a stack of overlapping curtains. Voyager 2 confirmed this complexity. It detected a foamy heliosheath, regions where solar and interstellar fields seemed magnetically connected. Charged particles, instead of bouncing cleanly off an invisible wall, leaked along these connections. The heliopause was not a sealed hull. It was a patchwork, stitched together by magnetic field lines that threaded from the solar interior out into the galaxy beyond. By the end of tonight, you're going to understand why that matters, because once the data from both spacecraft were combined with IBEX maps, scientists realized the heliopause is not fixed at all. It ripples, solar storms shove it outward, lulls in the solar wind let interstellar pressure push it inward. In some directions, its position can shift by several astronomical units over timescales of years. The edge of the solar system is no longer a hard shell. It is a flexible membrane, more like the surface of a living cell than a rigid wall. Cells have pores, channels, and gates. The heliopause has magnetic portals and pressure-driven folds where particles can slip through. And that is where the highway idea enters. A permeable, shifting boundary naturally creates lanes, regions where particles are trapped, regions where they are funneled along magnetic field lines, regions where they escape with surprising ease. No one predicts that the edge of our solar system will behave like an interstellar interchange, yet Voyager's data point directly to on-ramps, off-ramps, and feeder roads in the traffic of high-energy particles. Now, let's begin to trace those roads in the new maps. Those new maps do something else unsettling. They show that the bubble you thought surrounded the solar system is not a neat, symmetric shell at all. It's lopsided, twisted, wildly asymmetric. Before we get started, remember the textbook picture, a nearly spherical heliosphere, the solar wind pushing out evenly in all directions, a clean boundary where interstellar space begins. By the end of tonight, you're going to understand why that picture had to be thrown out. Voyager 1 crossed the termination shock at about 94 astronomical units. Voyager 2 hit it closer in, around 84. Later, Voyager 1 reached the heliopause at 121 astronomical units, while Voyager 2 crossed at about 119. Same star, same wind, different distances. That alone tells scientists the boundary is not a perfect shell. Then IBEX enters the scene, a small spacecraft in Earth orbit, quietly counting energetic neutral atoms from all over the sky. When those data are turned into a global map, the flux is not uniform. There are bright regions, dim regions, and that mysterious ribbon aligned with the local interstellar magnetic field. No one expects the outer heliosphere to light up in a band that tracks an invisible field threading through space. Yet that is exactly what the mission discovered. To make sense of this, models have to include more than just plasma pressure. They must fold in the orientation and strength of the local interstellar magnetic field, the field the solar system is currently ploughing through. The result is striking. Magnetic pressure presses harder on some sides of the heliosphere than others, squashing it in the direction of the incoming interstellar wind and stretching it along directions where the field and flow can slip past more easily. In these simulations, the heliosphere looks less like a smooth bubble and more like a distorted droplet, or even a croissant with two extended lobes. The heliosheath, that turbulent region where the solar wind has slowed but not yet yielded to interstellar plasma, does not have uniform thickness. In some directions, it is relatively thin. In others, it flares out and the heliopause surface bends and curves in complex ways. That distortion matters. Regions where the heliosheath is thin and the curvature is sharp become access points. Particles from interstellar space, especially high-energy cosmic rays, can follow magnetic field lines and gradients and reach the inner heliosphere more easily there. Other regions, where the sheath is thick and the boundary more gently curved, act as more robust shields, forcing particles to diffuse through a longer, more tangled path. The old idea of a uniform protective bubble collapses. Instead, the solar system moves inside a directional shield, with thinner and thicker sides that modulate cosmic ray exposure and space weather conditions throughout the solar neighbourhood. Tonight, we're going to see that this has a direct consequence for the hidden highway outside. An asymmetric heliosphere means the interstellar lanes around us are not evenly spaced. Some approach right up to those thinned regions, some peel away along the stretched lobes, concentrating traffic where the boundaries are weakest, and somewhere along those warped edges the next, even stranger feature is waiting to be mapped. Those warped edges are strange enough. Then IBEX turns on, scans the sky in energetic neutral atoms, and something impossible appears. A narrow glowing band wrapped across the whole sky. A structure no model predicts. No one expects a perfect sky-spanning feature to pop out of the data like a cosmic neon sign. Before we get started on what it means, remember what IBEX is actually seeing. It never leaves Earth orbit. It never flies to the heliopause. Instead, it counts energetic neutral atoms created when fast solar wind particles charge exchange with slower atoms from interstellar space. Map those ENEAs across the sky, and you map where the invisible battle between solar wind and galactic wind is most intense. Every pre-IBEX simulation says that map should look smooth, maybe with a gentle gradient. Instead, IBEX discovers the ribbon, a narrow arc where ENA flux is 2 to 3 times brighter than surrounding regions, cutting across constellations like a cosmic scar. By the end of tonight, you're going to understand why that scar turned out to be the most important lane marker on our new interstellar highway map. Follow-up analysis brings the real twist. When scientists compare the ribbon's position to independent measurements of the local interstellar magnetic field, a pattern emerges. The ribbon lights up exactly where that external field is perpendicular to our line of sight. Wherever the galactic field lines cross your view at a right angle, the ENA emission spikes. That simple geometric clue suddenly reveals the field's direction and even hints at its strength. In other words, the ribbon is not random decoration. It is a magnetic signpost. It traces where interstellar magnetic field lines are draped and compressed around the heliosphere, like streamlines of water wrapping around the bow of a ship. Where the draping is strongest, charged particles are guided, trapped and scattered, and that focused traffic produces the bright ENA glow. This turns a confusing anomaly into a powerful diagnostic. With the ribbon as a guide, scientists rebuild their models of the heliosphere's interaction with the galaxy. They adjust the tilt and intensity of the local interstellar magnetic field until the simulated ribbon lines up with the real one. They identify zones where particle exchange is most intense, where galactic cosmic rays leak in and solar particles leak out, and where the protective boundary of the solar system is thinnest or most porous. Tonight, we're going to treat that ribbon as what it truly is, the most visible lane marker on the hidden interstellar highway. A glowing billboard advertising the direction of the galactic magnetic field wrapping around us, pointing along the routes where charged particles, dust and perhaps larger grains preferentially flow. And just beyond those bright magnetic lanes, a darker, more complex network of currents and filaments is waiting to be traced in even finer detail. Those glowing magnetic lanes on the IBEX map aren't just pretty patterns. They hint at something far more radical. The solar system isn't sealed off, it's wired in. There are actual channels where the sun's magnetic field and the galaxy's field lock together and open a passage. Voyager 1 stumbled into one of those passages before it even left the heliosphere. In 2012, just inside the heliopause, its instruments recorded a sudden, dramatic change. The intensity of charged particles from the inner solar system dropped. At the same time, high-energy particles from interstellar space streamed in along certain directions with almost no scattering. The magnetic field didn't flip the way some scientists expected, but the way particles moved did. The team called this region the magnetic highway. On this highway, charged particles were no longer trapped by looping solar field lines that bend back toward the sun. Instead, the field lines behaved as if they had been cut and spliced, extending outward and connecting directly to the interstellar magnetic field. Along those lines, particles could stream freely, guided by invisible rails threading across the boundary. Tonight, we're going to treat that as more than a curiosity. It is the first direct sign of a connected route between inside and outside. How does such a corridor appear at all? It forms where heliospheric and interstellar magnetic fields reconnect or align just right, so they no longer oppose each other but merge into a continuous structure. Plasma physicists call it magnetic reconnection. Here, it is more than a textbook process. It turns the heliopause from a hard wall into a leaky membrane, carved by narrow, extended paths that cross from solar wind plasma into the interstellar medium. That has consequences. Along these connected zones, solar energetic particles from flares and coronal mass ejections can escape much more efficiently, draining along the highway instead of diffusing slowly through turbulent regions. At the same time, galactic cosmic rays, which the heliosphere usually deflects and slows, can penetrate deeper into the system, bypassing some of the shielding that protects the planets. No one predicts that the safest direction in space might depend on which magnetic lane you choose. IBEX quietly backs up this picture from its distant orbit near Earth. In certain directions, the energetic neutral atom flux is enhanced in ways that point to stronger exchange of particles along specific field orientations. Those ENA hotspots behave like signposts where connected magnetic regions funnel charged particles, convert some into neutrals, and beam information back toward the inner solar system. By the end of tonight, you're going to understand that these magnetic highways are not a metaphor. They are the literal roadways of the interstellar highway system, channels where traffic flows with minimal resistance between the sun's domain and the galaxy beyond. And just as with any network of roads, the next question is obvious. Where do all of these lanes ultimately lead? Now, let's begin. Those lanes don't just wrap around the sides of the heliosphere. They do something even stranger behind the sun. The place everyone expected to be simple and obvious turns out to be one of the most complex regions in the entire solar system boundary. For decades, textbooks showed a single, sweeping tail, a bright comet-like plume of solar wind stretching millions of miles downstream. The picture was clean. The sun plows forward, the wind streams back, and you get one long, graceful wake. No one predicts that when spacecraft finally map this region in detail, that elegant tail will almost vanish. When IBEX and Cassini built their all-sky maps of energetic neutral atoms, scientists went hunting for that glowing downstream beacon, a big bright enhancement where the solar wind piles up and then trails off into interstellar space. Instead, the ENA signal in the tail direction is faint, patchy, and surprisingly compact. The grand plume is missing. In its place is something shorter, stranger, and harder to ignore. This is where the simulations have to grow up. Early models treated magnetic fields as a minor detail. Add more realism, and the shape of the heliosphere changes dramatically. Now the heliosphere looks less like a comet and more like a distorted croissant, with multiple tail lobes and a stubbier, more turbulent wake behind the sun. The downstream region kinks, twists, and folds under the pressure of the local interstellar magnetic field. Each of those lobes is not just geometry, it's a separate outflow channel. One lane might be dominated by slower, cooler solar wind that has been processed in the heliosheath, another by hotter, more energetic particles that have been accelerated at the termination shock, and another by particles already mixing with the interstellar medium beyond the heliopause. Different particle populations, different histories, different connections to the galaxy. Think of it less as a single river and more as a braided river delta in space. The flow of solar wind reaches the downstream side and then splits into multiple channels, weaving around invisible magnetic sandbars. Some channels dive deeper into the local interstellar medium, some skim along the heliopause, some reconnect back into the larger galactic flow. By the end of tonight, you're going to understand that this is not decorative detail. It controls how radiation, dust, and even charged grains escape from the solar system. In highway terms, the heliosphere's tail is not one lonely exit ramp. Behind the Sun, the interstellar highway splits into several parallel routes, a multi-lane interchange where solar wind material is redistributed into the galaxy along distinct paths. No one expects a cosmic cloverleaf back there. Absolutely no one anticipates that some of those lanes might also funnel traffic the other way. Because if there are outbound routes, there may also be inbound ones. And the next discovery asks a dangerous question. What exactly can reach us by taking the fast lane in? So what exactly is out there to come screaming in on those fast lanes? To answer that, you need to know what the highway is paved with, and this is where Voyager quietly detonates another assumption, that interstellar space is almost perfectly empty. Before we get started, remember how uncertain the picture used to be. For decades, scientists tried to estimate the plasma around the solar system using starlight absorption, radio scintillation, and computer models. The numbers for local interstellar density and temperature wandered all over the place. Some models favoured a thin, hot medium. Others argued for cooler, puffier clouds. No one predicts that two aging spacecraft will settle the debate by listening for the faintest hiss of electrons. Voyager 1 loses its direct plasma detector before it even reaches the heliopause. Mission over for plasma physics, right? Not quite. The spacecraft still carries a plasma wave instrument, sensitive to tiny radio oscillations in the surrounding gas. When a solar outburst sends a shockwave racing outward, it plows into the interstellar electrons and makes them ring. Measure that ringing frequency, and you can infer the electron density even in the dark. Tonight we're going to stand with Voyager 1 in 2012, just beyond the heliopause, when those tones first come in. The inferred densities, around 0.05 to 0.08 electrons per cubic centimetre. Later events push that up towards 0.1. Higher than many models had dared to assume. Denser than the whisper-thin medium textbooks described. Suddenly, the space beyond the boundary looks less like a void and more like a very tenuous, but real, ocean. Voyager 2 crosses years later with its plasma instrument still alive and confirms the story. Similar densities, similar surprises. Combine those numbers with the magnetic field strengths both spacecraft measure, and a new picture emerges. The local interstellar medium is not a loose fog. It is pressurized, structured, and strong enough to squeeze and sculpt the heliosphere's outer skin. The implication is dramatic. The heliopause is not just where the solar wind runs out of breath. It is where two competing pressures meet. The outward push of our star and the surrounding interstellar plasma and field. Change the external density or magnetic tension, and the boundary flexes, ripples, and warps. No one expects a static bubble. Absolutely no one anticipates how patchy the environment turns out to be. Because the densities and field strengths are not the same in every direction. As Voyager 1 and 2 move along different trajectories, their measurements hint at gradients and jumps like crossing invisible weather fronts in space. The Sun is not drifting through a uniform medium. It is ploughing through clouds, filaments, and cavities on scales of tens to hundreds of astronomical units. By the end of tonight, you're going to understand why that matters for the hidden highway. Those clouds and filaments are the roadbed. Where density and magnetic field lines bend and bunch, lanes form, merge, and diverge around our solar system. The next question is obvious. What can ride those lanes efficiently, and how far can they reach? Those lanes are not just a cartographer's curiosity. Put everything together, and a pattern emerges that is hard to ignore. A flexible heliopause that ripples and breathes with the solar wind. An asymmetric heliosphere, compressed in front and stretched into a multi-lobed tail. A glowing E-Na ribbon wrapped around us. Magnetic highways that open and close. A structured interstellar medium flowing past like a galactic riverbed. Each of those discoveries started as a local puzzle. A boundary crossing here, an unexpected ribbon there, a density spike far beyond the planets. But when scientists step back, the message is larger. The solar system is not a sealed bubble drifting alone through empty space. It is wired into its surroundings. The heliosphere is a node in a network, a charged membrane plugged into the magnetic circuitry of the galaxy. Now let's begin to see it that way. Begin. The ENA ribbon traces where interstellar magnetic field lines graze the heliopause, channeling particles along preferred directions. The magnetic highways Voyager detected are places where those field lines connect directly to the solar magnetic field, letting charged particles stream in and out with far less resistance. The multi-lobed tail shows that even behind the Sun, flows are split, redirected, and recombined over hundreds of astronomical units. That means particles do not just leak randomly across a boundary, they travel along routes. Galactic cosmic rays, born in distant supernova remnants, can follow these large-scale fields, thread past nearby clouds, skim along our heliosphere's flanks, and pour down the magnetic highways Voyager briefly sampled. Neutral atoms can ride the same gradients, become charged, and rejoin the flow. Even dust grains, tiny but charged, can be steered over long timescales by this same invisible scaffolding. Tonight, we're going to treat this not as a static picture, but as a transport system. Over millions of years, those routes can link our solar system to neighbouring interstellar clouds, to the wake of ancient supernova explosions, even to the extended bubbles around other stars. From that perspective, the galaxy is not a random fog. It is a web of interacting heliospheres, bubbles and filaments, all exchanging particles and energy along shared field lines. No one expects interstellar space to look like a highway map, yet that is the conceptual shift now underway. Instead of a uniform void, scientists are drawing a galactic transportation grid where pressure, density, and magnetic tension carve lanes, junctions, and cul-de-sacs. The Voyagers are parked on one tiny off-ramp, while missions like IBEX and soon IMAP sketch the overpass from above. And absolutely no one anticipates the next question staying purely theoretical for long. If nature has already built a highway system between stars for particles, could future spacecraft learn to surf those same gradients? Could advanced propulsion tap into magnetic highways and pressure channels to move through the galaxy more efficiently than rockets alone? The data says the roads are there. The real mystery is whether anything more massive than a proton can ever learn to drive them. The data says the roads are there. But to know where the highway begins, you first have to decide where the solar system ends. That sounds simple. It is not. Before we get started, think about how the word edge gets used on Earth. The edge of a city can mean the last house, the last streetlight, or the point where the phone signal dies. Same place on a map, very different boundaries. The solar system works the same way. Different physics, different edges. Tonight, we're going to redraw that map. The most familiar edge is an arbitrary one, distance. Textbooks often talk about 100 astronomical units, about 15 billion kilometers from the Sun, as if there is a line painted in space. It is a handy round number. Spacecraft cross it. Mission press releases mention it, but nothing special happens there. No one predicts a sudden change in particles, fields, or radiation at 100 astronomical units. It is a convenience, not a frontier. The first physically sharp boundary is the heliopause. This is where the solar wind, racing outward as a hot, thin plasma, finally loses the tug-of-war with the interstellar medium flowing past. Inside, the Sun's wind dominates. Outside, the galaxy's plasma and magnetic field take over. Voyager 1 discovered this edge in 2012 at about 121 astronomical units, When solar particles dropped, galactic cosmic rays surged, and the character of the surrounding plasma changed. Voyager 2 crossed a different route in 2018 and saw the same pattern. That is not just a distance marker, that is a true plasma boundary. For space weather and particle physics, this is the meaningful end of the solar system. Inside the heliopause, storms on the sun sculpt radiation environments around planets and spacecraft. Beyond it, the rules are written by the galaxy. In the context of the interstellar highway, this is the crucial interchange, the place where the sun's outflow meets the galaxy's inflow and where magnetic field lines can connect local roads to the wider network. But there is another edge far beyond any spacecraft path, the Oort cloud, a vast, probably spherical halo of icy bodies extending tens of thousands, maybe up to 100,000 astronomical units from the sun. These comets are so distant that sunlight is a bright star, not a warming lamp, yet they are still gravitationally bound. Disturb one with a passing star, and it can fall inward on a million-year plunge toward the inner planets. Dynamically, as long as the sun's gravity rules their orbits, they are part of the solar system. Pattern interrupt. The solar system in this sense might be a light year wide, but its plasma bubble is only about 100 astronomical units. By the end of tonight, you're going to understand that there is no single edge. For light and warmth, the practical solar system ends where sunlight fades into the galactic background. For gravity, it ends at the outer Oort cloud. For comets, it ends where passing stars can finally steal them. For plasma and space weather, it ends at the heliopause. And for the interstellar highway, that heliopause is where our local road merges onto the galactic freeway, and where Voyager's tiny spacecraft first rolled across the ramp. Now, let's begin to map what that freeway actually looks like. Inside that freeway map, the old question comes back with new urgency. Are we actually safe in here, or just sheltered by coincidence? For decades, the heliosphere was sold as a clean answer. A bubble. Inside. Us. Outside. The galaxy. By the end of tonight, you're going to understand why that picture was comforting, but wrong in all the interesting ways. The shield is real. The solar wind really does carve out a region where the sun's magnetic field dominates, and that region filters the most dangerous high-energy particles in space. Galactic cosmic rays slam into this magnetic cocoon, and many are bent away, scattered, or slowed before they can reach the inner planets. Not all of them, not equally. The protection is uneven, and it depends brutally on energy. Lower energy cosmic rays are blocked far more efficiently, while the highest energy particles cut through the heliosphere like it is tracing paper. Now, let's begin to layer in time. The heliosphere does not have a fixed radius printed in some cosmic user manual. It breathes. Over the 11-year solar cycle, the sun's magnetic field flips, sunspots wax and wane, and the solar wind pressure rises and falls. When the sun is active, the wind is stronger, the magnetic field more tangled, and the heliosphere inflates, pushing the heliopause outward. During quiet years, the wind relaxes, the field simplifies, and the entire shield can contract by tens of astronomical units. This means the same point in interstellar space does not always sit outside the boundary. Sometimes Voyager is deeper in the heliosheath. Sometimes it is close to the heliopause. No one predicts a rigid wall. The data show a flexible membrane, pulsing with the solar cycle and responding to the local interstellar pressure around it. Then the new maps add another twist. Missions like IBEX revealed that strange ribbon of energetic neutral atoms aligned with the local interstellar magnetic field. Those field lines are not just scenery, they are the rails of the interstellar highway. Where the heliosphere's magnetic field connects to those external lines, charged particles can stream in or out along preferred directions. In some longitudes, the shield is effectively punctured, letting more cosmic rays penetrate. In others, the geometry can deflect or trap particles, strengthening the protection. For astronauts riding through deep space, that anisotropy matters. A mission to Mars during solar minimum, when the heliosphere is shrunken and the galactic flux is high, faces a very different radiation environment than a mission launched near solar maximum. Satellite designers bake this into shielding budgets and electronics hardening. Some climate researchers even explore whether multi-decadal changes in cosmic ray access could subtly modulate cloud formation and long-term climate, though those links remain debated and far from settled, so the updated picture is not a lonely solar system sealed inside a glass dome. It is a living, breathing magnetic shield, inflated by the sun, sculpted by the galactic wind, and plugged directly into a larger network of magnetic highways that thread between the stars. No one expects a simple inside versus outside anymore. The real story is how those connections shape what can cross the boundary and where that highway might take us next. So the picture changes. Instead of a fragile solar system sealed inside a glass dome, imagine a moving vehicle pushing through a storm on a dark galactic highway. The sky isn't empty. It's full of invisible rain, charged particles, magnetic fields, and interstellar gas sliding past in slow motion. Tonight, we're going to swap that old mental image of an island in a black ocean for something much more dynamic. For decades, textbooks showed the sun as a lighthouse, its solar wind blowing a neat bubble in a quiet sea of space. Isolated, self-contained, surrounded by emptiness. But the data from Voyager, IBEX, and soon IMAP say that picture is wrong in all the most interesting ways. Now, let's begin with the windshield. Think of the heliosphere as the front window of a car driving through heavy rain and wind. The solar wind is blasting outward from the sun, but the entire solar system is also ploughing through the local interstellar medium at tens of kilometers per second. From the sun's point of view, there is a headwind. Some droplets slam into the glass, others are deflected, skimming around the sides, curling into vortices in the wake. That is what the new maps suggest at the boundary. Energetic neutral atoms trace out where the galactic rain hits hardest, forming that strange IBEX ribbon wrapped around our system. The heliosphere is not a static bubble. It is a shaped flow, a blunt shield, with plasma and magnetic field lines draping over it like water over a moving car, guiding particles along preferred lanes. Now extend the analogy. Your car is not alone on the road. Every nearby star is also moving through this interstellar weather, blowing its own stellar wind, carving its own heliosphere, astrosphere, or magnetized cocoon. Each one is a different size and shape, depending on how strong its wind is and what kind of galactic headwind it faces. No one predicts they all look the same. In the local arm of the galaxy, these bubbles and wakes begin to overlap. Their boundaries touch. Their magnetic highways intersect. By the end of tonight, you're going to understand the sun not as a solitary island, but as one node in a crowded intersection of stellar influence zones, where charged particles, dust, and cosmic rays can be steered from one system to the next. Before we get started on the hard physics, picture a three-dimensional map. The sun's heliosphere is one glowing shell. Around it, other shells, the bubbles of Alpha Centauri, Barnard's star, Proxima, each threaded by filaments of magnetic field and plasma. Together they form a lattice, a mesh of connected regions and corridors, more like a web of overlapping neighborhoods than lonely houses in a void. This is the mental model that finally matches what Voyager felt as it crossed the heliopause, what IBEX and future IMAP see in all-sky energetic neutral atom maps, and what new simulations are beginning to predict. No one expects future textbooks to go back to that simple circle-in-a-box diagram. The real question now is, if our cosmic address is a galactic intersection, what exactly is travelling along those roads? And could something ride them far beyond where any spacecraft has gone so far? If there really is a hidden highway wrapped around the solar system, the next question is obvious. Could anything built by humans ever ride it? Not just drift through space, but actually use those magnetic lanes and plasma flows the way ancient sailors used winds and currents on Earth's oceans. Now, let's begin with something that sounds almost modest: trajectories. Tonight, we're going to treat the interstellar medium as more than empty background and ask how future probes might navigate it as a dynamic environment. By the end of tonight, you're going to understand why knowing exactly how the magnetic field bends, whether plasma is dense or thin, and how the galactic wind streams past the heliosphere could change how scientists design missions beyond the heliopause. Right now, Voyager is coasting on a simple gravitational fling. No steering, no course corrections. In the future, a probe leaving the solar system might choose its exit like an aircraft choosing a jet stream. Models already suggest regions where the interstellar magnetic field lines drape smoothly around the heliosphere, and regions where they kink, twist, and focus charged particles. A careful mission designer could thread a path through zones of lower turbulence to reduce radiation, or deliberately cross sharper gradients to surf natural electric fields for tiny but long-term boosts in speed. Then there are the sails. Not the sunlight-push solar sails already being tested, but magnetic sails and plasma sails that interact directly with the medium Voyager is now sampling. A magnetic sail would inflate a loop of superconducting cable with its own magnetic field, pushing against the charged particles of the interstellar wind. A plasma sail could use a cloud of ionized gas as a gigantic invisible parachute. No propellant, just momentum exchanged with the flow that IBEX and future IMAP maps are beginning to reveal. If those concepts ever leave the whiteboard, they will depend on knowing where the interstellar highway is fastest, where it is rough, and where it is calm. The same maps that show a ribbon of energetic neutral atoms might someday be annotated with tailwinds and headwinds for different directions out of the solar system. No one predicts a perfectly safe route between stars, but there could be corridors where cosmic ray exposure is measurably lower, where magnetic field geometry naturally deflects the most damaging particles away from a spacecraft path. All of this is speculative. The engineering is far beyond anything that exists now. But every precise chart begins as a scientific curiosity. The first coastlines were drawn by explorers who were just trying not to sink. The first heliosphere maps are being drawn by spacecraft that were just trying to survive a 5-year tour of the outer planets. Absolutely no one anticipates those crude sketches becoming the opening pages of an interstellar navigation atlas. Yet if that happens, Voyager and IBEX may be remembered not only for discovering the boundary of the solar system, but for tracing the first faint lines of a galactic roadmap, a chart that future missions will refine, extend, and eventually follow into the dark between the stars. From 1977 to that imagined galactic roadmap, the arc looks almost impossible. 2 spacecraft built with tens of kilobytes of memory and 23-watt transmitters leave Earth on a 5-year mission to the outer planets. Decades later, their faint signals are helping redraw where the solar system ends and how it connects to the galaxy beyond. Now, let's begin to pull that journey together. In the late 1970s, scientists picture the heliosphere as a mostly spherical bubble. Solar wind on the inside, interstellar medium on the outside, a clean boundary at the edge. Voyager races past Jupiter, Saturn, Uranus, Neptune, turning those distant planets from blurry points into worlds. But the real surprise waits far beyond the last orbit. When Voyager 1 crosses the termination shock at 94 astronomical units, and Voyager 2 at a different distance, the first crack appears in that simple picture. The solar wind doesn't just stop, it slows, heats, and piles up in a turbulent heliosheath. The boundary is not where models said it should be. The shape is not what anyone drew. The data hint that the heliosphere is asymmetric, distorted by the galactic wind it plows through. Then comes the heliopause, Voyager 1 in 2012, Voyager 2 in 2018. Both spacecraft record a sharp drop in solar particles, a jump in galactic cosmic rays, and a change in plasma density that screams, "You have left the solar wind's domain." But the magnetic field direction barely rotates. Prediction versus observation. Again. The old idea of a neat bubble gives way to something stranger, magnetically wrapped and embedded in a structured interstellar medium. Pattern interrupt. The most detailed map of this new boundary doesn't come from a probe at the edge. It comes from a spacecraft orbiting Earth. IBEX and soon IMAP watch energetic neutral atoms streaming in from all directions and discover a bright ribbon arcing across the sky, aligned with the local interstellar magnetic field. No one expects a glowing band tracing invisible field lines. No one predicts that this ribbon will become the signpost of an interstellar highway. By the end of tonight, you're going to understand that highway as more than a metaphor. Those magnetic field lines act like lanes, guiding charged particles, dust and energy around and through the heliosphere. Some paths bend tightly around the nose, some sweep into a structured tail, some thread directly into the galactic environment. Our solar system is not sealed. It is permeable, exchanging radiation and matter along these routes. So now you can visualize it. A layered heliosphere. Fast solar wind, shocked wind, helios heath, heliopause, then the denser, cooler plasma beyond. A ribbon in the sky marking where the interstellar field drapes around our magnetic shield. The sun not as an isolated captain adrift in empty space, but as one node in a wider galactic network, wired in by magnetic lines that span between stars. Tonight we're going to treat that as a new kind of self-portrait. For generations the story was simple, a lone star with its family of planets, drifting through a quiet void. The new map says something different. The solar system sails through currents, leans into a galactic headwind, and plugs into a web of connections that may stretch from one stellar neighborhood to the next. We are not drifting alone. We are part of a dynamic, interconnected highway system written into the magnetic skeleton of the Milky Way, and the Voyagers were humanity's first slow vehicles onto that road. We are part of a road system the solar system can't yet drive. Think about how improbable that is. 2 spacecraft launched in 1977, with computers weaker than a modern calculator and transmitters dimmer than a refrigerator light, have become the surveyors of a hidden interstellar highway, designed for a 5-year mission to study 2 planets. Still talking nearly 50 years later, more than 20 billion kilometers from home. No one expects that hardware to survive the cold, radiation, and micrometeoroid sandblasting of deep space. No one predicts that instruments tuned for the outer planets will end up measuring the plasma density and magnetic field of interstellar space. Absolutely no one anticipates that their faint whispers, combined with a small satellite in Earth orbit, will redraw the map of the solar system's boundary. Yet that is exactly what happened. Voyager 1 and Voyager 2, tiny spacecraft riding the last breath of their radioisotope power, are now beyond the heliopause. Their signals arrive at Earth with less power than a watch battery spread over a giant radio dish. But encoded in those signals are the signatures of a new medium, denser interstellar plasma, a shifted magnetic field, and a surge of galactic cosmic rays that had been held back by the solar wind. At the same time, IBEX has been sweeping the entire sky in energetic neutral atoms, turning invisible flows into a global map. Together those missions have transformed the heliosphere from a vague bubble at the edge of the solar system into a structured frontier with a heliosheath, a wrinkled heliopause, a mysterious ribbon, and tails that may trail for hundreds of astronomical units. By the end of tonight, you're going to understand that this is not just cartography, it is the first sketch of a galactic traffic pattern. Stand there in your mind for a moment, at the edge of the heliosphere. Behind you, the solar wind thins and cools. Ahead, magnetic field lines bend away into the dark, guiding charged particles along lanes that can stretch for light years between stars. You cannot walk there. No crewed ship can yet ride those routes. but the instruments have already gone, turning the unknown into a map with labelled regions, measured pressures, and traced flows. Tonight, we're going to treat that as what it is, a human achievement on the scale of the First World maps, except the world is a moving magnetic frontier between a star and the galaxy it sails through. Before we get started on the final part of this journey, remember that missions like Voyager, IBEX, and the upcoming IMAP exist because people choose to care about long, difficult exploration. And the next step on this highway, the one that might finally carry a ship between the stars, depends on what we choose to do next. Because by this point, you are not the same viewer who met Voyager at the launch pad. By the end of tonight, you're going to understand why scientists were wrong about our solar system drifting alone, how the heliosphere is not a quiet bubble but a wind-carved shield, and how a hidden interstellar highway wraps around that shield like lanes of traffic around a moving ship. You now carry that map in your head. The boundary is no longer an abstract line on a classroom poster. It is the heliosheath where the solar wind slows, the heliopause where interstellar plasma pushes back, and the strange ribbon and tail where energetic neutral atoms trace out magnetic lanes beyond the planets. Voyager flew through it. IBEX imaged it from Earth's orbit. IMAP is about to sharpen the resolution again, so imagine the next decade. IMAP watches the sky as the solar cycle flips, catching the heliosphere flexing and breathing. New probes dive outward on trajectories that no one predicts will reveal simple answers. Maybe a future Voyager-style mission threads directly along one of those interstellar field lines, riding the gradient in cosmic rays like a ship hugging a current. No one expects a 1970s spacecraft to discover a galactic road system. Absolutely no one anticipates what a purpose-built interstellar pathfinder might uncover. So tonight, somewhere beyond the orbit of every planet, both Voyagers are still drifting. Voyager 1 is 15 billion miles from Earth, threading through the local interstellar medium with its instruments still active, still sending back plasma density measurements that nobody on this planet completely understands. Voyager 2 is following a slightly different path through a slightly different magnetic environment, building the second data point for everything Voyager 1 sees. IBEX is still in Earth orbit, still mapping the energetic neutral atoms that trace the heliosphere's outer ribbon. IMAP is being assembled for launch. The map of the interstellar highway is still being drawn, one faint signal at a time. There is something steadying in that. The boundary of the sun's influence does not know it is being measured. The magnetic field lines that thread out into the local cluster of stars do not bend differently, because telescopes are watching. The cosmic rays streaming inward from the wider galaxy keep arriving on the same trajectories they have been arriving on for billions of years. And somewhere along those quiet, invisible lanes, the next discovery is already on its way. Some of it has been on its way since before the Earth existed. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.